Hello, everyone. Welcome to a lecture. It's not the conventional lecture where we'll be teaching things. It's just going to be solving some AMC problems from the 2020 AMC cycle, just to show you the thought process for how some of these problems can be solved. Just wanted to show motivations for solving them and how we would go about doing them. So that's basically just it. We're going to go over 5 problems from the 2020 AMC site that were particularly nice or were good for doing examples. So let's get started. If it'll work. Let me get the pen tool here. So first question here is from the 2020 AMC 10B, number 25, and 12A, number 24. Can I write on this? Okay. So it says let d of n denote the number of ways of writing the positive integer n as a product of n equals f1 times f2 all the way to times f of k. And where k is greater than or equal to 1. So the fi are integers where which are strictly greater than 1, and the order in which the factors are listed matters. That is, two representations differ only in the order of the factors that are counted as distinct. For example, a number 6 can be written as 6, 2 times 3, and 3 times 2. So this for the order matters because we can switch the order of these two numbers. And then so d of 6 consequently is equal to 3. And what is d of 96? That's what we want to find. First of all, it might be a good idea to find the prime factorization of this number. Then we can proceed. So 96 is equal to 32 times 3, which is 2 to the 5th times 3. I don't know why it's not letting me write. Okay, there we go. So there we go. 96 is equal to 2 to the 5th times 3. Now, logically, we want to see how we could do this, but first of all, let's disregard the 3 for a moment. It seems strange that the problem has this number, which is a power of a prime, and then this 3, which means that maybe we can organize 2 to the 5th in a nice manner. So let's try organizing 2 to the 5th in a nice manner. So let's say we have those 5 factors of 2 just here, and how many ways can we put these into f1, f2, and so on, such that they're greater than 1? Well, one thing that comes to mind is the ball and earn method. And for that, we could just drop partitions. And then like if we had 2 partitions, then this would be F1, this would be F2, and this would be F3. And then the order would also be counted because this would correspond to 2 times 4 times 4. But we could also divide this up like this. So we can put a divider here, a divider here, and that would correspond to 4 times 4 times 2. And the only thing we'd have to guarantee here is that there is a 2 in each group. And so we could count this, basically we could count this splitting into 1 group, 2 groups, 3 groups, 4 groups, and 5 groups. Those are the number of groups we can split into. So we could do casework with the ball and earn method. We still have the 3 here. And we want to figure out how many ways there are to insert the 3 into this expression if it's possible. And well, we could, let's go on with this example here and let me go ahead and erase these, all this here, because we no longer have to deal with it. And we'll still stick with this example where if I have a pen, can I get this? We'll still stick with this example where we have F1, F2, F3 is decided by these partitions. Well, we could add 3 into one of these partitions. So let's consider like we're splitting this into 3 groups for now, and we'll generalize it to n groups. Uh, we could multiply the 3 into any one of these groups. So if you put the 3 here, this would turn from 2 to 6. If you put the 3 here, it would turn from 4 to 12. If you put the 3 here, it would turn from 4 to 12. So there's 3 ways to do that. But we can also have 3 standalone, and we could put that uh, before the first group, right? We could put it in between the first group and the second group, because if we multiply these, they're going to be like integers. So there's going to be like F1, F2, F3, and we want to arrange 3 somewhere, basically. This is a better way of saying it, probably. So let's say you had this group, and then you can see that there are, well, 4 ways to rearrange it. And basically, if you had let's generalize this to n. Here we picked three ways because there's three groups, so we could multiply the three into any of those groups, and that would give us n ways if we were to generalize it to n. And here, if we were to put the 3 as just its own number, then we can arrange this. This is going to be a 3. This is going to be n groups. And so there are n plus 1 ways to organize it. So because of that, we're going to get 2n plus 1 ways to insert the 3 once we have a number of ways to do this. Split the number of factors of 2 into groups of n. Well, n groups. So let's carry out the computation for that. If I can move on, can I? There we go. So let's return to the example. So basically, we're going to do casework on n. It can equal 1, 2, 3, 4, or 5. And there are 2n plus 1 ways to insert the 3. This is for the 3. So let's start with n equals 1, logically. Well, there's only one way to organize this into one group, is just to put all the factors of 2 together, so 2 to the 5th. And consequently, there are three ways to organize it. You can either, as we've said before, we can put the 3 here, or we can put the 3 here, or we can multiply the 3 in with the 2 to the 5th. So that gives us three ways to organize for n equals 1. We may have to use extra slides, so let me just write this down for future reference. Next is n equals 2. So now this is going to get a bit more complicated. Well, we want to guarantee that there is 1, 2 in each group because the fi sequence is, they're each greater than 1. They can't be 1. So since there's two groups, we can just put a 2 in each of them. So now we have 3 2's we want to organize. And we have one divider that's going to select. That's going to partition them. And so, yeah, if you want to think about this like this, basically I just had a partition. So this is group 1, this is group 2. I put a 2 in here and I put a 2 in here so that we can guarantee that they're greater than 1. And then I would just partition them. I'd take the other 3, I would partition them. Sorry, I would partition them like this. Like this is an example of a partition. And so I would put that, this means I would put 1, 2 here, and this means I would put 2 2's here. And so that's how it works. Well, the way to do this is, you can see that it's 4 because there's 4 places to put the divider, or you can just do 4 choose 1 equals 4. Since there's 4 ways to do that, and we have to incorporate the number of ways to incorporate the 3, so it's going to be 4 times, if you put 2 in here, it's going to be 5. 5 equals 20. So there's 20 ways to do that for 2 groups. Next, I'm going to try to fit the third group in here. I think I can. Similarly with the third group, we're going to proceed the same way. We have 5 2's, but since there's 3 groups, we're going to put a factor of 2 in each group to guarantee that it's greater than 1. So now we have 2 2's and 2 dividers. And the number of ways to do this is, well, 4 choose 2 is equal to 6. And the number of ways to incorporate the 3 is 7. So we have 6 times 7 is equal to, know why it's doing that. 7 is equal to 42. That's the value for this case. Let's keep on going with our casework here. If you go on to n equals 4, we want to guarantee that there's a 2 in each group. So there's really only 1 2, and there's going to be 3 dividers because we have 4 groups, right? Let me just make sure. Yeah. So this is similarly just going to be 4 choose 1. So there's 4 ways to organize the 2's. And to incorporate the 3, it's going to be 2 times 4 plus 1, which is 9. So that's going to be equal to 36 ways. So yeah. And finally, our last case, n equals 5. There's only one way to partition the 2's into, well, 5 groups. Just put a 2 in each group. So there's one way to do that. And there's 3 ways to incorporate, well, there's 2 times 5 plus 1 equals 11 ways to incorporate the 3. This would be 11 times 1 is equal to 11. So now we can get our answer. So you've done our cases. So our answer is just going to be the sum of what we got in each case. It's going to be 3 plus 20 plus 42 plus 36 plus 11. Just adding this up. So this is going to be 23. This is going to be 78, 11, 23 plus 89, 100, it's going to equal to 112. So let's see if that's one of the answer choices. It should be. And it's this, if I can find my cursor, it's this answer choice right here. It is A. And so we're done with this problem. It's just a simple balls and urn problem, ball and urns problem. Uh, and yeah, so for this, basically what we did was we took a restriction here to 3. We disregarded it for a second just so we could work with an easier problem. And then we figured out how to incorporate this restriction back again and count like that. And so that's just a strategy you can try on the AMCs if you have a problem like this. Let's move on to this problem. 2020 AMC 10A number 21 and 12A number 19. So, uh, we have that there exists a there's a unique strictly increasing sequence of non-negative integers, a1, a2, so on to ak, such that 2 to the 289 plus 1 over 2 to the 17 plus 1 is equal to 2 to the a1 plus 2 to the a2, so on and so forth. So what is k? They're basically asking for the size of this sequence. Well, first of all, you see that 289 is 17 squared. So for simplification, let's let a equal 2 to the 17th. Then we can write this as a to the 17th plus 1 over a plus 1. Now you can actually know this does divide into it and it will give you a sequence. But you can also see that it's actually like the finite infinite geometric series formula. We should know that that is the initial term times r to the n, well, r to the n minus 1 over r minus 1. You can also write this as 1 minus, it's like, you can also write this as a to the 1 minus r to the n over 1 minus r just because negatives. And you can see here that this actually looks really familiar with this. First of all, the initial term seems to be 1. So now we're left with 1 minus r to the n, or 1 minus r. And we can see that it seems that r is equal to negative a. And it checks out, because then that'll give you 1 plus a to the 17 over 1 plus a. It takes a bit of practice recognizing that, but you can see that it does seem to follow that. So what is this? What can we get from this? Well, we know it's a finite geometric series. It starts with 1. It has common ratio a, negative a, and it has 17 terms. Let's move on with this knowledge. Uh, so, as you can see here, we can write that as 1 minus a plus a squared minus a cubed plus a to the 4th, so on. You can go on to minus a to the 15th plus a to the 16th. This fits the condition. 1 is initial term, negative a is a common ratio, and there are 17 terms. So this isn't exactly what we want. As you can see here, this is a sum. We have like an alternating sum and difference thing over here. So how are we going to proceed? Well, one thing you might notice is that a power of 2, so I'm going to use k plus 1 for the example, minus 1 for a positive integer k. You can write it as 2 to the 0 plus 2 to the 1 all the way up to 2 to the k as a sum. So we see a lot of adjacent terms here. So if we can get like a power of 2 minus 1, as we know that a is equal to 2 to the 17th, we define that. If you can get an a minus 1 or an a squared minus 1 or an a cubed minus 1, it would help us out a lot. So let's group these like these. So you get 1 plus a squared minus a plus a fourth minus a cubed all the way to a to the 16th minus a to the 15th. Now, you can see that we can actually factor out an a in each group. And that'll actually give us a minus 1. Well, I mean, you can factor out the highest power in each group. And you can see that it gives you the a minus 1. And that's what we want. Because we know that, just finish writing this up. We know that a is equal to 2 to the 17th. So if we plug in 2 to the 17th again, we get 1 plus 2 to the 17th, 2 to the 17th minus 1, plus 2 to the 51, to the 17th minus 1, and so on up to 2 to the 15 times 17, whatever that is, times 2 to the 17 minus 1, so on. Well, as you know, we can write this as a sum of, well, 17, 17, 17 powers of 2. 2 to the 0 plus 2 to the 1, all the way up to 2 to the 16th. So that means if you were to write that, you can actually just do that straight up. If we were to substitute that in, that would give us 16 terms here. And we could just substitute that in for every 2 to the 17th, that minus 1 that shows up. In that case, you may worry about overlap, and there's actually no overlap, because the highest term in each would be 2 to the 17th times 2 to the 16th here, which is equal to 2 to the 33rd. But that's not going to touch the next term, which is 2 to the 51. So quite simply, we just have 17 terms for each block that's here. And if you notice, there are 17 terms. We've actually left out the 1 here. So there's actually 16 over 2, 8 such groups that have 17 terms. So that is 8 times 17. We don't want to forget the 1 because we can write the 1 as 2 to the 0. And it does say non-negative. So our answer is going to be 8 times 17 plus 1. Now, 8 times 17 is going to be 136, plus 1 is equal to 137. So our answer is 137. And so that is how you would go about doing that problem. Moving on to our next problem here. Here's the 2020 AMC 12B number 22. You're given this problem. It says, what is the maximum value of 2 to the t minus 3t times t over 4 to the t for real values of t? Well, how would we do this? First of all, we can see that we're trying to maximize a product. And usually when you see that, you think AMGM. But sometimes that might not always be the case, but you can see here that we have 2 to the t minus 3t, and we have a t here. If you were to multiply this expression by 3, then we can turn that into a 3t. And as you know, 2 to the t minus 3t plus 3t is equal to 2t. And since there's a 4t in the denominator, it seems that this could lead to some cancellation. So AMGM might actually work here because the sum of this, we can actually cancel the linear term and get a 2 to the t. So let's try it. Let's try AMGM. So as I said before, I'm going to work with, I'm going to apply AMGM, first of all, on 2 to the t minus 3t over 4t. Not 4t. It's 4 to the t. Give me a second. If I can find the... Huh? There we go. Okay. 4 to the t. And I'm going to use it on... I made another mistake, didn't I? It should be 2 to the t minus 3t over 4t. And I'm going to also do 3t over 4 to the t, because if you sum these up, then 3t's cancel. And so let's apply that. So basically by AMGM, we have that a plus b squared equal to 2ab. That just reminds me, I wanted to go over this. AMGM only works for positive real values. And it says for all real values of t. The reason why 0 and negative values of t don't work is if you actually plug in negative values of t, you can see that the 2t minus 3t is going to be positive. Well, this is going to be negative. So it's actually going to give you a negative sum. If t is less than 0, then the product is going to equal 0. If t equals 0, then the product is 0. And these are not the maximum values, because you can just take a random value. Let's take like t equals 4, because I think that's when it becomes positive first. You get 16 minus 12, which is 4, times 4, which is 16, over a positive power of 4, and that's positive. So that means anything 0 or below is not the maximum value. So I just wanted to debunk that before we moved on. It's important to know that AMGM only works for positive reals, so we had to test those just to be sure and just to make sure our solution is rigorous. So using this AMGM, we can go ahead and sum. Oh, sorry, this is going to be 2 square root of AB. My bad. Uh, and you're going to have plus 3t over 4 to the t. The greater or equal to 2 square roots of, well, the product of the two. 2 to the t minus 3t over 4 to the t, and 3t over 4 to the t. And now if I were to go into the next slide, uh, before I go on, I'm going to rewrite this product, and you can see that the sum here, these and these cancel, so it becomes 2 to the t over 4 to the t. So moving on, if you continue, we get 2 to the t over 4 to the t is greater or equal to 2 square roots of 2 to the t minus 3t. I'm just going to simplify this a little bit. 3t over 4 to the 2t, because we're multiplying, there are two 4 to the t terms in the denominator, so we multiply them together so we get 4 to the 2t. Logically, we want to square, and that's going to give us 2 to the 2t over 4 to the 2t. I just want to clarify this. This is going to, it's going to be equal to 1 over 2 to the 2t. Let's just, which equals 1 over 4t. Let's just do that for simplification purposes. So if we square that, so it becomes 1 over 4t is equal to 4 times 3 times 2 to the t minus 3t 3, I mean t, it's t. 'Cause I brought up the 3 just to show that there's a 4 to the 2t. And this is very similar to our product in the original problem. It just has an extra factor of 4t in the denominator. If you multiply both sides by 4t, you're going to get 1 is equal to 4 times 3 times 2 to the t minus 3t. This should be a linear term. 3t times t. I'm going to clean this up a bit just in case you were confused. And since I multiplied the both sides by 4 to the t, it should be greater than or equal to 4 to the t. And this is our product. This is the thing that we're trying to find. So if you divide both sides by 12, you get that 1/12 is greater than or equal to our value. I'm just going to call it x because I'm too lazy to rewrite that, but that's what x corresponds to. And basically that says that x is less than or equal to 1/12, which means that 1/12 is our maximum value. It's attainable when 2 to the t minus 3t is equal to 3t, and, well, 2 to the, yeah, it is equal with that. And you can see that those graphs will intersect if you're worried about if you're worried about it being not achievable. You can test it for yourself because those graphs will intersect at some real value of t. So the equality case does exist. It is achievable. So for that reason, our answer is 1/12. So that is how you do that AMC problem. Let's move on. And we'll move on to the 2020 AMC 10A problem number 22. So for how many positive integers n is less than or equal to 1000 is this true? The floor of 998 over n plus the floor of 999 over n plus the floor of 1000 over n not divisible by 3. Recall that the floor of x is the greatest integer less than or equal to x. This seems a bit intimidating because you have 3 floors, and usually, you know, uh, if you were me, I would be scared of just 1 floor. But there's 3 floors in this problem. But we kind of want to break it down here. So let's see when it's divisible by 3 and when it's not divisible by 3. And there are 3 ways this could happen. Let's say that the values of each of these is the same. X, x, and x. Well, that's going to equal to 3x, and it's clearly divisible by 3, so we don't want to count that. Let's say that the values are different, like they're x, x plus 1, and x plus 2. Well, the sum of that is 3x plus 3. And that's also divisible by 3. So we can't have that. And the only other case is if two are the same and one's different, so you can do x, x, x plus 1, or x, x plus 1, x plus 1. And you can actually see that if you sum these up, this is 3x plus 1, and this is 3x plus 2. They're not divisible by they're not divisible by 3. So these are the ones we want to count. But when do these occur? Well, you can see that you you want n to divide one of these three numbers. If it didn't, like let's say n divided like 997, then before we do that, let's just say that, well, n is like greater than 2, because for that reason, then, well, hmm, that would be a good example to show this. I just want to think about this for a second. If n is a 4 or something, if n is large enough, then all these are going to be different. Uh, wait, all these are going to be the same, sorry. Unless, n divides one of these, then it's actually going to be different than what we were thinking about. But, like, if n is large enough and it divides something beforehand, all three of these are going to be equal. Uh, and the only way these three can be different is if, and you can see why, because obviously it's going to work for small values, only for n equals 1. And that's because it becomes 998, 999, and 1000. And, well, so let's see what happens if n divides each of these, because that's the only way it'll work. If that's the only way we can achieve these cases. Because, I just want to say again, the only way you get a shift in the middle of the sequence is if n divides one of these, because it'll tick the floor value up by 1. So let's see, if n divided 998, then the sequence would also be x, 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 unless n is equal to 2, in which it would actually become x, x, x plus 1, but we'll see why that's the case, and that's actually because n also divides 1000. Uh, and n equals 2 does work. You do have to count n equals 2. Uh, so other than n equals 2, and n equals 1, of course, we already showed that, if n divides 998, they're going to be the same value. If n divides 999 for a value other than 1, then the shift will occur at 999, and then we get what we want. And if n divides 1000, then given it's not 1, the shift will occur here. And actually, with the respect to 1000, if 2 divides into 1000, you can see that this becomes 499, this also becomes 499, and this becomes 500. So n equals 2 does work here. So what this seems is, it seems like our answer is, we want to find the number of divisors of 999, because dividing into 999 gives us something what we want, and the number of divisors of 1000, because the divisors of 1000 give us what we want as well, except for 1, because 1 doesn't work. Everything past 1 works, and you can see why, because the differences will be greater than like having 3 different values. As you can see with 2, there's no way we're going to have 3 different values unless n equals 1. You want to disregard 1. So basically, we want to count the number of divisors. So let's let d of n be the number of divisors. So we want to count d of 999 plus d of 1000. And we want to subtract 1 from each of these counts. If you actually count it twice, we count once here and once here, so we want to subtract by 2. And there's no overlap between the divisors here because they're relatively prime. They're consecutive integers, so they are relatively prime. So we don't have to worry about overlap. Well, we could just straight up calculate this. 999, you know that's equal to 3 squared times 111. But 111 is not prime. That's going to be equal to 3 cubed times 37, and 37 is prime. So this has 4 times 2 is equal to 8 divisors. 1000 is an easy prime factorization. It's 2 cubed times 5 cubed, which yields 4 times 4 equals 16. This yields 16 divisors. So our answer is going to be 8 plus 16 minus 2 is equal to 24 minus 2 is equal to 22 values of n that work. So it's going to be A. So that is how you do that particular AMC problem. It's just testing some values and seeing when this function shifts. Let's move on to the 2020 AMC 10B number 21, 12B number 18.
So it says that in square ABCD, points E and H lie on A, B, and D, A respectively, so that AE equals AH. Points F and G lie. Actually, let me just mark this. So it's important information. Points F and G lie on B, C, and CD, such that, well, respectively, and points I and J lie on EH, such that FI is perpendicular to EH and GJ is perpendicular to EH. So see the figure below, triangle AEH, quadrilateral BFIE, which is this one right here, quadrilateral DHJG, which is this one right here, and pentagon FCGJI, which is this one right here, all have area 1. First of all, let's just note that since they all have, these four figures have area 1, the area is 4, so the side length is 2. S equals 2. So we want to find Fi squared. Let's think about how we would find Fi squared. First of all, you can see that we can actually split this into two trapezoids. So if we knew Fi, if we wanted to find Fi, we would probably need to know what Ji is. Because we can find this length is just part of the diagonal. Because we can find this length right here. But we would need to know Ji for this to work. But to find Ji, we would probably need to find Hj. And it seems like finding Hj is kind of painful. Uh, you don't really see, if you experiment this, there's not going to be really any nice similar triangles to use, and it's overall going to become painful to find Hj. Pythagorean theorem is not going to work because Gj is kind of a value that's equal to Fi that we want to find. So let's try to find another solution. So let's look at this quadrilateral that involves FIEB. The angle measures are, well, they're 90 degrees here, 135 here, because this is 45, 90 here, of course, and it's also going to be 45 because this is going to be 90 here, and it's going to be 45 here. But so interestingly, you can see here that if we were to extend this, right, this forms a 45, 45, 90 triangle with side length Fi. So one thing you might try to do is, well, let's let these intersect at K because the next point up. Maybe you want to try to find the side length KF. Well, to find the side length KF, you need to know what FE is. And I don't think there's a nice way to find FE because if we knew what FC was, then I think we would be able to probably try to find HJ. And even then, it still becomes a bit complicated. But we can see that, well, we can also tell based on the area. And why we want to look at the area is, well, we know the area of this chunk already, it's 1. And we can easily find the side length Fi if we know the area of this whole triangle. And we know that the area of this is 1, so we just have to find the area of this. So this is also a 45, 45, 90 triangle. We need to find what, kind of covered everything up here. But that should be, what is that? That's B. So we want to find side length EB then, because then that would give us the area of this particular triangle. Triangle KEB is what we want, the area of that. Well, to find EB, we would want to find AE, because EB is equal to 2 minus AE. Well, we know that the area of triangle AEH is 1, which means that you can find the side lengths pretty easily. Since it's an isosceles right triangle, it's going to be root 2 and root 2, because if you multiply those, it's going to be 2 divided by 2, it's going to be 1. So A is actually equal to root 2. So we actually know what EB is. It's 2 minus root 2. So we want to find the area of now KEB. Well, that's just squaring 2 minus root 2 and dividing by 2. And that's going to give you 6 minus 4 root 2 over 2 is equal to 3 minus 2 root 2. So that's the area of, well, it's the area of this triangle here, triangle KEB. So we know the area of triangle KIF is equal to BFIE plus area of KEB. And that is going to be equal to, we know the area of BFIE, that's 1. We know the area of KEB, we just found it, it's 3 minus 2 root 2. This is equal to 4 minus 2 root 2. Well, how would we find the area of this? What's the area of KIF? Well, the side length is Fi, so just simply Fi squared over 2, because it's isosceles right. Well, The problem actually asks for fi squared. So we can just multiply by 2. This implies that fi squared is equal to 2 times 4 minus 2 root 2. It's actually equal to 8 minus 4 root 2. And that is this. It is this answer choice B. And we are done with this problem. And that is basically all I have to say. Uh, in terms of a handout, I will have one. It's just the solutions to the 5 problems we covered in this lecture. I'll just be sending you a handout with that if you want to have the solutions in a written form, if you find that easier to uh, understand. And yeah, I'll see if I can have that in the link in the description. Don't forget to join the CNCM Discord server. Link will also be in the description. And do remember to like and subscribe. And I'll see you for the next lecture.